My name is Dr. Huggins. I'm an assistant professor in the Department of Kinesiology at the University of Connecticut. I work at the Corey Stringer Institute, and it's my pleasure to welcome Justin Jacobs. Justin is a PhD, principal research statistician for Sandia National Laboratories, and a remote researcher for the National Basketball Association. Graduated from the University of Maryland, Baltimore County with a PhD in statistics prior to working as a faculty at Coppin State University within the Department of Defense. During his tenure at the DoD and National Laboratories, Justin worked on various projects fusing statistical analyses, data science, and intel analysis in helping solve some of the nation's most challenging problems, ultimately earning his agency's first ever Presidential Early Career Award in Science and Engineering, a Career Award, and an ODNI Medallion Award. Aside from his work in national security, Justin has also served either as a consultant or a remote researcher and a full-time researcher for multiple NBA teams since 2013. Most recently, the Houston Rockets from 2018 through 2020. So please welcome Justin Jacobs, and he's going to be presenting on a Square-Integrable methodology into play registration for NBA tracking data.
All right, thank you. So there will be an exam on everything that was just said, so I hope you're all paying attention. Thanks for having me early this morning. I kind of wanted to give insight of how we think about what can seem like really complex ideas in statistics, show how they apply to problems, and then extract out what's really going on. The core component here is to kind of show you the actual mechanics of it. So this is going to be a little bit of an academic lecture, so apologies in advance. But don't be intimidated. I will show as much as humanly possible at each step. So we are going to go pretty slow, but I want to show you something really cool. Let's see here. Which way can I do this? There we go. All right. So what we're going to do is we're going to start with a non-sports example. So at the end of this story, I want you to keep reminding yourself of this non-sports example, because this non-sports example is going to carry out through the entire theme, even though we might seem to deviate quite a ways away. And if you know a little bit about me, huge Marx Brothers fan, so you're going to see a bunch of Marx Brothers quotes as we go through. The non-sports example is going to be dealing with like facial recognition. So, Groucho Marx says, "I never forget a face," but in your case, I'll be glad to make an exception. And what we're going to talk about here is iris scanning and registration. So I'm not sure if you know this, but your iris is actually like a snowflake. It effectively builds a unique barcode to identify who you are. And what happens is when you're born as a baby and when you come out as a baby, your rods and cones haven't quite formed fully. And over those first 3 months, they start to fracture and break. And that's what builds this unique pattern. So let's suppose there's a situation where you are a child who's just gone through this process. A couple of years into your life, you're abducted and then you disappear off the face of the earth effectively, right? So it's not like you're abducted and they say, "Oh, you're somewhere in the neighborhood." Like, you're just gone. There's 30 years that pass. How do we still keep finding these folks that have been missing? This is actually a methodology that we came up with that actually does find people in the wild. So we can use the irises to extract out those barcodes and then say, "Are you a match?" So since this process ends 3 months in, if I have a photo of you at 2 years old, and then all of a sudden I see a photo of you pop up online in some general repository, I can run this algorithm, extract out the barcode, and see whether or not you're that person. And it's pretty amazing that we can actually do this and find missing children. So for your example here, if you can see, I get over here. Can you guys see my mouse? If anyone wants to hop on.
Yes, we can see your mouse.
Awesome, great. So what we do here is we have an edge detection algorithm that's outside of the point here of what we're going to look at. But we have an edge detection algorithm that says, all right, here's the iris. And we're going to take this little area in between, right, the actual iris, and then we're going to unravel it and then run math magic over it. And we're going to extract out effectively this barcode, which is in the upper left corner. And that's what's going to be that registration, or that scan that we can use for registration. So once we have a collection of barcodes, we can actually run them over each other and compute the Hamming distance. So when I say run them over each other, wherever you're going to slice, because it's circular, wherever you're going to slice, that's going to be the left endpoint. And we want to, that left endpoint is not going to be the same everywhere. The easiest way to explain it is if you're faced on the slice, let's say it goes down, but if you're tilted slightly, the slice is no longer down, it's off to the side. So what we do is we'll take the barcode and just slide it across and compute Hamming distance. When we do that, we're going to get a number of pixels that match in this case. So this distribution, we actually get like this bimodal distribution that pops out. This left-hand distribution is the probability of a non-match. And most people don't match because everyone's got, their own unique barcodes. In fact, most people have two barcodes. And those barcodes don't even match. Your left and right eyes don't match either. We're going to have a very hot spot. But we actually see this like 0.8 region kind of pop out. So the x-axis here is the percentage of bits that match, and the y-axis is the resolution of the photo. And as the worse resolution occurs, you see the probability of matching kind of get worse and worse, which is kind of what we expect. But if we get some pretty nice resolution photos, we get a really nice separation boundary. So we developed this back in 2011. I say McGarvey et al. I'm part of the et al. In this situation, building these distributions out and ensuring the robustness of the filters. We were able to apply this into the National Center for Missing and Exploited Children, and this algorithm has been off and running and doing fantastic stuff. So if I put this process together, what I've done here is I've taken an iris, and I apologize if you're creeped out by eyes, but I take the iris, I do an unwrapping, and here's where I do that segmentation. So this is the actual picture of the iris. And then I run this filter over it. And this is what's called a Gabor filter. And I don't want to like stress you guys out about this. I just want to show you what the pictures look like. But it's a particular filter that tries to look for the relationships and frequencies between the grayscale components of the iris. And those relationships, those hard shifts in the grayscale components, ones that should be separated greatly do get separated. Some that are kind of off will get lumped together. Think of it kind of as like a weird sigmoid. Like the sigmoid tries to push out far away components and pull in close components. Meaning if I have a grayscale value of like 200 versus 205, they'll kind of get together. And then a value of like 105 versus 210, they'll push them farther out. But here, I don't want to just do that. And this is why I said it's a weird sigmoid. What I want to do is I want to look not just for jumps that kind of get closer and farther away, but I also want to look at some where I might want to pull them together that are farther away, meaning that if I look at 2 to 3 pixel segments, and even though I have a 205 and 210 next to each other, that 205 might be linked to a couple 100s, and that 210 might be linked to a couple 200s. And now I want to push those far away. So it's kind of doing this multi-layering effect. And that's what helps build this barcode. And then we just run Hamming distance. So it ends up being an incredibly simple algorithm because all you do is extract out the image. That's kind of the little hard part. But you extract out the image, you unwrap it, you convert to grayscale, you run a Gabor filter, which is a function call and some parameter tuning, and you run a Hamming distance. So the question is like, could we do something similar for this? Because we've seen this work very effectively for registration of children or even adults. Could we see if this works in the sports world? So what we're going to do is we're going to try and build, instead of using a Gabor filter right away, because you guys don't know what a Gabor filter is, and I can't tell you easily what a Gabor filter is. So I think all of us are at a loss for trying to use it. So let's try and build up a methodology that makes sense so that when we do get matches, we can start to explain why does this match. The Gabor filter doesn't really give you that. It just tells you it is a match. So what we're going to do is we're going to start with the frequency space. And the quote here is, you pay us a little, we'll be a little tough. But if you pay us a lot, we'll be a lot tough. And that's a Chico Marx quote. The idea here is that if you put a little bit of effort into the frequency decomposition algorithm, you're going to get a little bit of help. you're going to be able to represent that function a little bit. But if you put a lot of effort into the frequency decomposition algorithm, you're going to get a lot of power. So if you're familiar with the Fourier series, then you've already got a leg up. But if you're not, you're going to learn some things today. So we're going to start with a simple numerical analysis example. What we're going to do is we're going to take a function f, and I'm going to convert this to s because I'm used to saying s for signal. But we're going to have this function little f. And this function little f is going to be our route that's being run, whether it is in football or hockey or basketball. If we have tracking data, you have routes. And what we want to do is take this f of x, and we want to represent it in some frequency space, which we're going to call like big F. Okay, so we're going to transform this collection of track paths and convert to some fundamental frequency. So the way we're going to do that nasty looking integral is we're going to do it by example. We're going to, sensitive, there we go. What we're going to do is we're going to take this function here, and let's suppose, for the sake of argument, we are looking at a Little League game that has tracking data, and here's a kid who's just literally running serpentine down the field. I pick this function. We're going to cheat a lot today because I want to show you the mechanics, and we'll discuss in the real world how this really works. But let's suppose we can represent the serpentine route as 3 times cosine plus 10 times sine with a frequency of 7 minus 3 times cosine with a frequency of 11. And that's going to be our signal. In the real world, we don't know this. We just see the path, so we can approximate this. But let's suppose now we know this. And when we convert over the Fourier series is actually a particular solution of the second derivative of Euclidean space. So the way to think about that is we know the distance between 2 points is a straight line. How do you define a straight line? You do it by saying that the second derivative is equal to 0 everywhere. So if I solve that the second derivative equals 0 everywhere, then I solve that function, I do the second derivative of a function in Euclidean space. So the d squared f equals negative f kind of thing. I get sine and cosine as the solutions. So these sines and cosines actually form an orthonormal basis that will be able to represent the entire space in Euclidean space. And what I care about is these b of k's, a of k's, and a naught. So what I'm going to do is I'm going to take this function and rewrite it in its basis, and I need to figure out what those coefficients are. So the way that works is I get this nice little result. It's the Fourier integral transform. All I have to do is take each fundamental frequency or its basis element for some frequency k, multiply it by the signal, and then compute this integral. All right, and this is pretty straightforward. This is Calc 1 at this point. So let's actually do that. So we're going to do a naught. Remember my s of x. So it's s of x times cosine 0 of x. So it's just the integral of s of x dx. I go and put in s of x, and I can compute this integral and it equals 0. So a naught is 0, and you can go ahead and verify this at home. Now, if I go and I'm going to pick A3, and I pick A3 for a reason. So S of X times cosine, I think I goofed here. Oh, yeah, I goofed up. This should be a 3, so apologies. So this is cosine of 3x. When I do this integral for cosine of 3x, is that right? Oh, no, I did this right. This is A1. Ooh, geez, I'm sorry, guys. That is my fault. I copied 3 to 3. So this is A1. It should be A1, yeah. Sorry. So I do the integral of s of x cosine of x. When I do this integral, you can verify that this is going to equal 3. So I know that, so this is actually the first Fourier coefficient. So if I get this 3, I get 3 cosine x. And that is actually the first part of s of x. So if I go and plot that, that's my approximate run of the route. And that's not good. It's really not good. I get the general mean path, but I have nothing with the serpentine process. But if I go and do the other levels of these coefficients, right? I know, because I set this function up the way it is, I know that the first Fourier coefficient is going to be 3. I know that the 7th Fourier coefficient under sine is going to be 10. And I know the 11th Fourier coefficient of, come on, stop clicking, of the 11th fundamental frequency is going to be -3. And you can go and verify that at home. And what happens is this green dashed line is going to be the first Fourier coefficient component plus the third Fourier coefficient, or seventh one. And then with red, it's going to be the 11th. And you see that the red just masks the entire blue. So we'll end up with a perfect fit here. That's fantastic. The perfect fit should happen. We pick the function that matches the fundamental frequencies perfectly. So from there, what we're going to do is we're going to apply this to an actual path. So we're going to cheat a little bit here, and I'll explain what we're going to do. And we're going to do sports. So Zeppel-Marx quote is, "You can't have a good football team unless you have good football players." Zeppel-Marx was a GM, obviously. But here what we're after is we're going to have this particular track. And how I'm going to cheat is I'm going to make sure that the track doesn't self-intersect. Means that you're not going to come backwards. It is an actual function. And the reason I'm doing that is because we want to be able to represent this this path in the Fourier space. When they come back and self-intersect, it doesn't work anymore. And in fact, we have to do something completely different. We have to move to like two-dimensional or temporal domain versions. So with this path, we can now represent the downfield location as the x-axis, and then a cross field is going to be their y-axis. And we want to be able to characterize this route, right? Because we're going to think of that iris problem. We want to build like a barcode for it, and then we can use that barcode to do whatever statistics we want to do. So what I'll do is I'll compute the first integral, and that first integral is going to be the integral of my particular function times 1, right? Because cosine fundamental frequency 0, cosine 0 is 1. So I'm going to do the integral of this path. Now, I don't know this path, right? All we see is just a collection of xy components. So when that happens, this integral that I'm trying to compute, this constant coefficient, has to be done numerically. So I have to use a numerical solver. So I'll use trapezoid rule or Simpson's rule. And when I do that, I'll get a coefficient A naught. So I plot A naught. All right, there we go. That is the 0-order Fourier series approximation of the route. And that is terrible. So we're not anywhere close to the route. It doesn't even give you the mean average of the route. Like it's just a straight line that's off by like 10 to 20 feet. But if I go to the first 10 levels and compute that numerical integration for each of those 21 first coefficients, and then I multiply them by the basis function, all of a sudden you see I'm now seeing the path as the mean trajectory of the Fourier representation. And I can keep going, and you'll see this just start to connect. And this is pretty cool. Like we're like, all right, this is fantastic. I have a representation. And I have a signature that's associated with this. And I'll show you quick what it looks like. That's the signature of the path. That's my iris barcode. All I have to do is take this guy and then run effectively Hamming distance against it. And I can search all tracking data in this space and find all those routes almost immediately. But there's a little subtle problem here. The first problem is not all routes are the same. So if I've got this player to run this route again, then he might come out on this bend an extra 2-3 feet. And the question is what happens there? This is a global effect. This is a global approximator. So if I have a small change on the bend here, I'm going to see changes out at the beginning of the route. And it's understandable, but it's not desirable. So what'll happen is in the coefficient space, I'll see these guys adjust a little bit, but I'm also going to see these big components, the big fundamental frequencies, those will adjust too. And so we really want to find like more of like a local, a localization And the reason this occurs, that ringing will occur out here, is back again to these equations right here. These cosine k of x's, sine k of x's. If we have a small adjustment in that s of x, that's going to throw this entire cosine of kx a little out of whack. This a of k is going to change accordingly. So when we multiply ak by cosine k of x, and that's what we're plotting, when we put that on, this slight adjustment is going to be affecting this cosine function, which operates over the entire path. So the Fourier series is not the way you want to go for doing play registration, but this is like the ground zero of getting onto what we actually do, which is apply a localization-based approach. And the most common localization-based way is to use wavelets. I've done the first three Marx Brothers. The fourth Marx Brother is Harpo, and if you know anything about Harpo, he doesn't really speak. So honk honk. Here we go. So the wavelet model is going to take effectively the Fourier setup. This is why we start with Fourier. And instead of writing the function f of x, we're actually going to use a different type of basis. And we call this a multi-resolution basis. And what multi-resolution means is that in the Fourier series, we have the big fundamental frequencies like the constant coefficient or the one period sine wave that covers the entire space. But we also get smaller squares. So we have like the higher frequency components, but instead of covering the entire space like cosine k of x does, we're going to look at like little sticks, little square regions. And I'll show that in just a moment. But that gets represented by this type of chopping up of the space, the sample space. So the way of thinking of multi-resolution is I have a big square that operates and I want to see what happens to the big square, but then inside I have little squares. And inside those little squares, I have even smaller squares. So I'm getting like varying sizes of resolutions, hence the multi-resolution. And one such construction we'll use, and this is like the most simple, is the Haar wavelet. And I'm going to use the Haar wavelet because it is discontinuous at certain spots, and the pictures look really nice when we do see them. And the Haar wavelet has two components. It's called a father wavelet and a mother wavelet. Oh, man, sorry, when my mouse moves, it kicks the slides for some reason. This is the father wavelet here, and this we're going to operate over the unit interval because it's simple to recognize. So we have the father wavelet here, and then that is just a constant function 1, and then the mother wavelet here is it's a piecewise constant function where I have a -1 that operates over 0 and 1/2, and then a positive 1 that operates over 1/2 to 1. So we'll show the picture in a sec, but what's happening is that I'm looking at a big square and splitting it into two smaller squares where one is a -1 and the other is a +1. And then because of, which way are we going here? There we go. Because of this multi-resolution that I'm using here, it's 2 to the j, there we go. Then I can index this by j and k, and I just keep taking each half interval and splitting those into positive and negative ones. And what happens is this actually builds me an orthonormal basis, just like the sines and cosines did, but I now get this locality, this ability to capture locality. And I can rewrite my signal or my route or my function in the exact same way that the Fourier series is. And I have to just compute these coefficients. Computing the coefficients is exactly the same as the Fourier series. I just do the convolution and take the integral. You just have, there's only one subtle thing here is you have to remember that there's a coefficient that's going to normalize this function. So I'm assuming that these are actually normalized. But I can extract out those coefficients. Alpha here is called the scaling coefficient. That's like that constant function. And then the betas are going to be the detail coefficients. And that's what's going to adjust the different heights of the basis functions. All right. So all we have to do is compute those again. Again, we have to do numerical integration when we're out in the wild, but here we're going to do it in using real functions. Actually, no, I actually do this with the route. So we'll see the numerical result. All right, so this is what a hard wavelet looks like. So this line here, that is the father wavelet. That's the constant function that goes through the entire domain. And then the first mother wavelet, remember, is -1 for the first half and +1 for the second half. And if you notice, they're not quite -1 and +1. They're actually adjusted to be the corresponding height. And it's a little trippy when you look at this picture, because the father wavelet's actually at 1/2. He's not at 0, and that makes sense because he's got to have some weight to him. So don't get hung up on the distance between the father wavelet and the mother wavelet. But this is that -1 over the first half. That's that +1 over the second half. And then the second set of mother wavelets are these blue ones, and I'm splitting the first half of the interval into a -1 and +1, of course, scaled for orthonormality. And then the other half, I have yet another. Now, here's where it gets a little tricky. When I go and fit a function, if I can go this way, when I go and fit this function, identify the coefficients, it's over the psi of jk's. So what's not happening is I'm not fitting it for this guy. I'm fitting it for this guy and this guy simultaneously. All right, so that's a little bit more of a challenge here to try and connect those dots. But as they do fit for this one, this left side, the -1 here, gets split again into a smaller resolution. And that smaller resolution is going to pick up the detail that this blue wavelet is not going to capture. And that's where we're getting our locality. So here's the fit of the wavelet structure. So this is the father wavelet in the top left. It actually looks like a mean constant route. That's way better than the Fourier series, at least in my opinion. It's still terrible, but it's a good fit for the mean at least. Then we go to the level 0 wavelets. We've included that this red one right here. So that's with the red mother wavelet. And we get this step function. And we start to see, as we include more and more mother wavelets, we see everything start to converge on the path, to the point that when we get to the level 7 wavelet, we've almost got this thing pretty much nailed. And fortunately, there's enough curvature here that we see the step function running up. So we still do see it's actually a step function and me not just plotting the orange on top of the blue. But we get ourselves a signature, and that is the signature of the route. And we can use this as our barcode and just run it over as if it's a, run it over all routes with this Hamming distance to be able to extract out the different routes. So not only do we get like the spatial resolution or the spatial information, the local spatial information, but we also get this multi-resolution. So the way that I've stacked this is based on what's called a coefficient number. So the father wavelet is actually 0. The first level, the 0 level mother wavelets, the first level mother wavelets, they're down here around, like 1 to 3 or something like that. And then the detail coefficient numbers, the smaller segments of those little sticks or those little rectangles are out here. And as you see, a bunch of these are effectively all 0. And that kind of makes sense because there's parts of the path that are relatively flat. And once it's flat and we've got it pretty much captured, that those new portions of the wavelets aren't going to introduce anything important. But if you ran Serpentine, you would see these guys kind of triggering and doing a little dance. Now, here's the really cool thing about that. If I have, we run this route again, and it comes out a little bit farther here, we'll see a little bit of change in the father wavelet. He might shift slightly down, right? It's not going to be huge, but the more important thing is that these guys over here are almost completely unaffected. And the guy who gets affected are going to be the ones, it'll be this wavelet here. So this right-hand wavelet. And then when we get to this level 2 wavelet picture here, the guys who's affected are just these two. And these guys are pretty much all the same. So if we do have a big change in the route, or if there's different routes that are the same, if there's different trajectories that represent the same route, we're able to still capture those routes. And it'll be within variation. And you have to build a statistical test to capture that. And that statistical test is like that iris barcode bimodal distribution that I showed you before. All right. So So I showed you how to do it with a particular route. Now we're going to expand this out to basketball. And there's actually a fifth Marx Brother. So if there's one thing you can take away, if you know the Marx Brothers, you always hear like the three or the four Marx Brothers. There's actually a fifth. So Gummel Marx, he says nothing. He's in none of the movies. But we're going to expand this out to basketball. And we started with this. So what we've built is a non-parametric methodology for comparing two trajectories from tracking data. This is just like the iris problem. I have two irises. I want to know if it's the same person. So I build this methodology to extract out a unique barcode, doing signal processing, and then I run a statistical test over it. Here, we're going to do the same thing for tracking data. We're going to do a frequency decomposition. We're going to put it into a non-parametric domain. We're going to then apply a Hamming code or some statistical distribution to be able to say that these two track paths are the same. And we showed the Fourier series to get those coefficients. That's like a traditional way to do it. And it's a good segue to get you into wavelets. But the wavelets are what's going to capture the spatial properties. And we also get the multi-resolution. So there's deviations in the paths. You know, we actually capture some of that without doing global changes. But remember I said I cheated. We used a track path that didn't self-intersect. And in reality, these paths do intersect. So what we have to do is we have to move to a two-dimensional domain. And that gets a little bit more challenging here. So what happens is that we're going to chop up the space, and we're using the Haar wavelets still, but we're going to chop up the space into a series of rectangles. And this is going to be wavelets, a level 2 wavelets. This is a level 2 wavelet here. And it's just going to keep chopping up more and more and more. So what will happen is if we run a particular play, let's just say there's a lift, right? So if we run a lift, that comes up the side of the 3-point line from in the corner. You're just going to see these two boxes interacting. If you see it down here, you're going to see it across 3 different boxes. If you see it here, you're going to see it on a hand, like what is it, 4 or 5 boxes, and it's going to keep getting smaller and smaller. But I don't want you to take away like, oh, we're just going to count how many things are in the box. It's not that simple. What's happening is we're coming back to here. Remember, each box is related. So each of the boxes is going to be each branch here. So when we looked at the upper left-hand corner of that Dallas Mavericks court, that's like one box is this branch. But remember, this branch doesn't get estimated alone. It gets estimated with the box next to it. So that's going to be similar here. So if I have a path that's going here, I'm not only going to look at this is a +1 and this is a -1, let's say, but I'm also going to look at this is a +1 and this is a -1, and this is a -1 and this is a +1, and you're actually going to get like a 4 choose 3 combination here, 4 choose 2 combination, and the number of coefficients kind of explodes. That's fine. We can still do that computation. But we have to be very careful that this is not just a box counting thing. And that Gabor filter that I showed you is basically what we're reconstructing, even though it's going to be a 2-dimensional Haar wavelet. But you saw how like it was a 2-dimensional picture with the iris codes and how it kind of went up and down and left and right. That's the same thing that's happening here. So if I was to take a Bucks Ram play, so this is a play they ran hundreds of times last season. So Bucks Ram is they run a player just inside the free throw line, comes down, set screen at the charge circle. Player comes up, set screen at top. So that's kind of a Ram screen. Bucks Ram is they set it with 2 very particular players, such that this screener comes down and that screener comes off the roll. If we go and look in the coarse wavelet grid, we see that we're affecting 1, 2, 3. We find trajectories that are affecting 3 boxes here, and we're finding that affects 2. So if I see a bend, if we run this play multiple times and this guy sets the screen a little bit higher, if he sets the screen higher, we're going to see a different type of bend to his screen or his trajectory, but he's still operating in these 2 boxes. So you're just going to see the segment of points coming across. You can do the numerical integration, and you'll see that these coefficients aren't going to change dramatically. However, in the more finer case, you're going to see those coefficients change quite a bit. The good news is that even though these coefficients change quite a bit, you're going to get the deviations measured here, but you're not going to say it's not the same path because of these type of wavelets that will help out. And I'm making, it looks like a big jump that's here, but this is the difference between these two is several. This is like a level, this is a level 2. This is more like a level, I'm just gonna guess, like 6 or 5. So, you know, you're gonna have a lot of levels in between. So don't think that it's just a jump between left and right. But we can build the signatures for this, and then we can go and look at all segments. Now, segments and do the Hamming distance, and then whatever guys have a high probability of matching across the spectral coefficients, then that's our play. So it's a way to basically do lookup, right? That's what registration is. So that's the two-dimensional case. Now, the natural questions that come out of this is, what is like a stopping and starting criterion? How do I build plays? So I've just talked about 2 trajectories here, right? So I have one player goes up, so I'm going to get one signature there. I have one player comes down, that's a signature. What we miss here is the temporal information. So this screen has to happen before this screen, right? Because if they don't happen, it looks kind of goofy. So you're going to see this guy come and then this guy go. So the way that we do that is we build a waterfall plot. And the way to do a waterfall plot is one way to do it is we set the temporal domain going north and south, and then east and west is going to be the spectral coefficients. So as the time goes, we're going to take each row is going to be like a frame, effectively, and a frame being a sample segment of tracking data, and then we're going to put the coefficients for that particular frame. So what you can do is you can go backwards, you can lead backwards to some stopping and starting criterion for the player. The obvious one that pretty much everyone that I know that does this uses is they look at the velocity of a player. So if the player starts to come at rest or hits some sort of acceleration criterion, that will be the signal to end a segment. And then when that player starts to pick up steam, maybe some high load component, or they just say velocity gets bigger than X, then they start a new segment for tracking that particular player. So you can build those segments. You're going to have a running waterfall plot for the entire period of play, and then you can just build a window that searches for like a RAM screen, because you know roughly how long a RAM screen is. Put a little padding in there, and then you can just run that Hamming distance from left to right, just like we do for irises, and you'll see the play pop. But the north-south would be the temporal. The left-right would be the wavelet coefficients. So it'd be the signal like this that are going left-right. And then you're actually going to have a third dimension that comes out. And this is why I didn't want to like display what the coefficients would look like for this thing, because it'll look really confusing when you plot them. But coming out at you are the different players, because you have 5 players running simultaneously. So you're effectively building like a tensor. And then your Hamming distance is taking over the tensor space. The good news is it's actually pretty straightforward. It's a sparse setup, so you can write a pretty clever way to do that. So that's how we would register plays. The important point from this talk, again, was just to show how to do the integration. And you can swap out the numerics for it to show what an orthonormal basis looks like and how we convert a signal to an orthonormal basis. So we kind of have that in hand. We know what we could do for the next steps. The natural questions from that point is, okay, cool. Is this a powerful tool? And the big takeaway from this tool is it is powerful, meaning that it does get you results. It is interpretable. So if you do see 2 plays are the same, you can actually crack it open, look at the coefficients, and be like, okay, well, these are the coefficients that are different. That tells me that these basis functions are a little off. What are those basis functions? Okay, it's the high curvature component. that tells me to look at, say, the acceleration. That might tell me intuition of how much does this player actually turn himself in a play. And you can work with the performance team on understanding how well players can read by looking at the shifts of shoulders, but we don't have shoulder data in basketball. So it's one way to start inferring body position. But it is a computationally exhaustive approach. So it is slow. It is very slow. And in 2013 days, when we started building this, it was even slower than what we can do now with GPUs and parallel processing. But we can use algorithms like what's called lifting. So we can use lifting algorithms to more quickly identify the coefficients, but we do sacrifice some of the interpretability in doing that. The other natural question asked is, what's the benefit of doing something like this versus a neural network, like a convolutional neural net? The benefit is we get interpretability, and in convolutional neural networks, you lose a lot of the interpretability. And you can start misdiagnosing plays. If your job is to just classify plays, I would encourage you to use convolutional neural nets. But if your job is to diagnose plays, where prediction is no longer king, like you want to be able to predict, but you need to be able to explain, then convolutional neural networks are not really the way to go. If you do a different style of neural nets, some folks will just build boxes and then do heat map counting, like they'll count how many times a player was in a box and run a neural net over that. You've sacrificed the orthonormal basis requirements. You'll probably get a good prediction, but again, you're going to fail in interpretability. Right. So that's the other thing is like with curve matching approaches. I know there's a few papers out there about curve matching. Sorry, I'm seeing all of these chat pop-ups. For curve matching approaches, trying to align those coefficients takes a great deal of effort. So with trajectories used, you have to identify the stop and start times and the start location, and then the associated parameters of the curve. So you get a great interpretability out of those algorithms, but they're very sensitive to changes in the distribution. So multi-resolution becomes an issue for them. But that's pretty much all I got here. So I guess I should open the floor for questions. So I appreciate everything that I appreciate you guys having me here and allowing me to ramble my way through the talk at 6 something in the morning.
Yes, thank you, Dr. Jacobs. Any questions that we have, please make sure you put them into the chat. Dr. Yan, did you want to go through the questions or would you like me to do that?
You go, Rob. Thank you.
All right, so we do have a question for me from Lyle Danley, which I will answer separate to this. But there is a question here from Mr. Zhang. It says, thanks for your interesting presentation. I wonder if you could give some more details on the interpretation of the coefficient and the K parameter.
Oh, sure. Yeah, apologies if this feels like a fire hose. I wanted to get as much information out there as possible to tell the story. Typically, when you learn Fourier series in undergrad, it's between 2 and 4 classes. So a 10-minute fire hose is not quite enough. All right. So each K is effectively the frequency. So if I have K equals 0, K equals 0 is just going to be a straight line. If I have K equals 1, I'm doing cosine, so it's actually up here. It's going to be just that usual cosine function, but you're just going to see that just one period through. And then if I have 2, you're going to see 2 periods. So the K is effectively the number of periods that go through the space, the domain. So here my domain is like 0 to 10. Because I have a sinusoidal function, and I know it's a sinusoidal, actual sinusoidal function by construction, that tells me that I can integrate over negative pi to pi. But in reality, if I'm over like 0 to 10, I should be putting 0 to 10 in here, and I should be putting in whatever that period is here. So it's really like 2 divided by the period. So I would have 2 over 10. So I should have like a 1/5 here. And that will actually pull out those coefficients. All right, that was the K part. What was the interpretability? So if I get a A0, so like for instance here, I know I have a 1-period cosine, like a 1-period cosine builds this, and I can realize it. And again, I apologize for this. This is the first Fourier coefficients. This is A1. I actually see that cosine period come through. And so that's that K1. Now, if I go for the sine 7, I'm going to have 7 periods that are ringing through here. And 10 is just the amplitude. So when I look at the coefficients, the interpretability is telling me how much weight do I have of that frequency. So this tells me that I have like 3 units worth of a period 1 cosine function. In the wavelet domain, it's the best way to put it. In the wavelet domain, the alpha 0 is going to tell me how much weight exists for this. So let's suppose that we have a flat function that's coming through here. So it's like 0 all the way until it moves. Then I expect all of these coefficients here to offset whatever the first father wavelet's going to do. So if I see a 0 function and then I see like a y equals x function out here, it's this father wavelet's not going to be 0 because there is a positive weight here. The function goes up like this. So it's going to find wherever that average is and put it. And let's just say it's right here. Then I know that the blue is going to pull this 0.5 back towards 0 because I need to estimate that 0. And then I know that these blue guys will do a really good job of it. Like they're going to probably flip and have whatever the approximate value of this to pull down. And then these black portions, if this pulls it all the way down to 0, everything below it is going to be 0. So I know immediately I've captured the locality of this region. And I can go and look at those coefficients and I'll see them all as 0. So if I see a bunch of zeros within a subset, because it's called a multi-resolution basis, if I see everything in the sub-resolutions to be 0, then I know that I have a locally flat position, which means my player's running in a straight line at that point. And approximating straight lines is, we can already do that. But keeping that idea in mind now tells me I can start that these coefficients that are a little different are actually capturing the curvature of the play, which is effectively how much that player is bending, how quickly they're turning. It gets us into the subtleties of the actual player reaction capability.
We have one more question here from Kevin. It says, do you think it is possible to create a 1-number catch-all metric in basketball?
No. No. I think they're always fun, but no. It's the job in basketball is not to rank players with a single number. Ultimately, you have to say how much a player is worth or valued, X amount of dollars over so many years kind of thing, because that's ultimately how you put players on your team. But you need a lot more that goes into that effort, and Catchall is going to miss how well a guy boxes out, how well a guy disrupts passing lanes. If you optimize for one aspect of the game, you're going to undersell other players. So 1-number metrics are fun for bar discussions, but they don't really they're not the most important thing.
Dr. Jacobs, in response to your first question, there was a follow-up from the same individual. It says, thanks for your explanation. And I also would like to ask how it could be used as guidelines for basketball players in real basketball court or coaches. A kind of curious question. So going back to your coefficient and K parameter interpretation explanation.
Could I ask how to, I don't know how to interpret that question. It's like guidelines, like like to try and instruct coaching staff and players, or what does guidelines mean?
Mr. Zhang, if you wouldn't mind adding, maybe helping to detail out that question.
So if it's my interpretation, as he starts to put it in, if I interpret it as like, how do you relay these results to a coaching staff or players or someone who's interested, like say a front office is interested in quantifying, then you do not, under no circumstance do you take any of this work and go and put it in front of a player or a coach or anyone but pretty much yourself and the analytics person you're working with. What you do, or what I've done in the past, is you work with another analyst or you work with your director and you have a discussion about, all right, this is what I'm seeing, this is how I interpret it. How do we want to frame this to have that discussion? And more times than not, like when I started talking about like this is how a player curves, the next logical steps that we do is we go and, since we now know exactly where those plays are and we can find those plays without having to search video, we can go to the video because we now know when they happen and extract out those plays. And then we say, okay, so we see what the subtle differences are in our coefficients. What do we see in the play that matches to that? And we'll somehow convince ourselves that that might be the right answer. And once we put together a good story of, okay, we see this bend radius that's coming out, and we might convince ourselves that, oh, this is how the player is navigating a particular screen. Because I was showing you offensive player trajectories. I'm not showing you defensive player trajectories. So if it's just offense only, that curvature, when we pull the video, it's like, oh, these screeners are taking an extra step left, and they're doing that to disrupt the action. And in these cases, the screener's not there. The screener is behind the player doing a chase. And we can now say, okay, well, what does that mean for that player to be setting those screens? What is it that they're picking up on? And then we'll go to the next layer of analytics, which is how does that affect whether or not we make that pass if it's an off-ball action? Does this lead to a shot? So if we have the action with no screener, it's out. Do they shoot? Do they not shoot? And we can start building like a diagnosis of how does that action disrupt our plays? But we wouldn't know that screen would be the case until we saw that deviation and say, okay, well, what's really going on here, and pull the video. So we would then craft that story to come back to the coaching staff saying, hey, we're noticing this type of action. Have you seen this? 9 times out of 9, the coaching staff already knows that action's occurring, but we're already armed with all the supplementary material of this is what happens when that action's occurring. And we can now color in the details of our probability of pass goes down 56%, which then translates to we're like half as likely to make those passes. And this is what happens next. And those little dialogues allow this coaching staff to be like, all right, video team, go back and check to see how this defensive player interacts with our team. And then they'll come up with their scheme to either change it if they think it's detrimental to their game plan. If it's not detrimental, they'll be like, all right, that's cool. Thanks for the knowledge. Keep up the good work. And that's pretty much where this would enter itself. But I would, if you're showing this model to a coach, you are in such the wrong direction of having that conversation.
I actually have a question for you. As an athletic trainer and someone who's constantly trying to, prevent injury and or, maybe highlight areas of dysfunction that I can work on through rehabilitation and or with the coaching or strength conditioning staff to improve a player's performance. Can you speak to maybe an example where your work has maybe assisted in that realm, or the behavior of a player as they approach, a specific move within basketball or on the court?
Not with this work necessarily. This work was pretty much specific for trying to find plays without having to write 7,000 filters for each different play type. And find them robustly. There are other ways that we've done this. So If I do look at a trajectory, there's some areas where I've looked at trajectories. It would be the next level after doing this, but it's to look at like how do players navigate screens. That's why I brought it up, because I've worked on that quite a bit. But there's a newer algorithm that came out from Carnegie Mellon. I think I'll give them props, whether or not they made it or not. But it's called part affinity fields. And it basically is modeling the joint connectedness of a player, and you can actually see like their limbs move around. And there's some work that I've done where I've tinkered with their algorithm to try and build distributional tendencies of players, because you can actually see them like twist when they're going around screens, and you can see like how much acceleration of their shoulders like twist when they get hit when they're coming around the screen. And it was curious because, you know, the first guy I always look at is Steph Curry, because he gets just watch him on a play, even if he doesn't have the ball, just watch him get rocked on some of these screens. Like he'll come in sorry, he's on defense usually, but these guys will come in and hit him when he's on defense, and you'll see him just spin hard. Whereas like you see another guy like Eric Gordon, he doesn't get hit that hard. And the question is like, could we identify like we use loads sometimes to measure how much an athlete is burning energy out on the court, but like loads don't capture how much these guys get rocked. And it's like, we found like we've tried building like energy methods to see how much energy, or energy models, like work models, to see how much energy is expended by a player. And we've tried to say, all right, well, we don't know their heart rate, like we don't know their internals, so we can't quite measure it. But let's just say the amount of rotation is just some amount of work, and we'll do the physical model and treat them like a simple system, and then just add that work on. And then we'll look at things like their field goal percentage, or their plus minus in a play. And when I say plus minus, I don't mean points. I mean their amount of speed versus the speed of the play. So if guys are like zipping down the court and one guy is like a -3% or -30% for speed, that means the play's moving fast and the guy's trotting behind the play. He's probably tired. He's probably given up on the play. And we want to try, we looked at to see if those guys are getting hit. If they're getting hit and we're seeing that decline in those numbers, like their negative differential in speed, their field goal percentage, or their field goal plus, if we see those drop, then that might tell us that we need to get that guy out, or more importantly, how do we re-scheme our defense so he's not getting hit as hard? But that's like the closest that I get to the performance side. Rehabilitation, I haven't quite worked with on that.
Okay, thank you. There is one other question here from Nick. It says, how much total impact do you think maximizing play calling has in NBA basketball?
It depends on who your players are. I mean, if we go to 1989, what was the play called? Give Michael the ball and get out of the way. It depends on the personnel. There are some teams that are just phenomenal at scheming, but sometimes the talent of a player will over-dominate the scheme. So it really depends from situation to situation. If you're more of like a middling team who doesn't have a breakout player that can just take over a game, and I don't want to, I'm hesitant to name team names because, I don't want to put any teams on blast. But if you don't have that team, then schemes, at least just a simple scheme, like a first action, like I'll put one on blast. So for Houston, one thing that we always wanted to do in Houston is we always wanted to run pistol. Every chance we can get, we wanted to run pistol because that would disrupt the perimeter defending guards. And if we could disrupt them, then that allows us to get quick open looks early or creates driving lanes to attack. And if that didn't happen, the next logical thing after that was to reset and set up rim run when we had Clint. So we know that those actions were going to occur, like out of 100 possessions, you're going to see each of those like 70 times. But that wasn't like the first scheme. After that, it's kind of like, all right, diagnose how the defense is. We have our set methods to go and attack. And at the end of the day, James is going to do what James is going to do. He's going to read the play. Chris and Russ were going to do the things that they needed to do. and they knew how to adapt. They knew how to play within D'Antoni's scheme. But schemes are pretty important. But it really depends on the roster.
All right. Doesn't look like we have any more questions at this time, and I believe we are at our time for the end of this session. So, Dr. Jacobs, thank you so much for your presentation. And I will turn it back over to Dr. Yan.